Continuing with complex numbers, we're going to talk about polar form and Euler form, different ways to write complex numbers. What you guys already know of a plus bi, that is the rectangular form, aka the Cartesian form, something that can be, placed within a coordinate plane. Okay, polar form is another way to represent the same number, and Euler form is another way as well. So we're going to be talking about those two forms today. Like I said, Cartesian form is z equals a plus bi, aka rectangular form. However, any point P that lies on a circle with the center of 0, 0 and a radius of r has Cartesian coordinates of r cosine theta, r sine theta. Okay, take it back to the unit circle here. You have your circle, you have a point that's on your circle. Remember, x represents cosine, y represents sine, and technically, depending on the radius of that particular circle, you can essentially find the coordinates of any point that's on that circle. So that's where that's coming from. Therefore, because of that, a complex number that's represented by the vector OP can be written as z equals r cosine theta plus I r sine theta, that I being the imaginary I from back up here. Okay, this can also be written with the r factored out in these two different ways. Yeah. This is polar form. This is polar form. The cosine theta plus I sine theta can be represented in a more shortened and condensed way. That would be this or CIS theta. That is what cosine theta plus I sine theta is in a more condensed way. And so your complex number z can be written as the modulus of z times CIS of theta. Okay, so again, the absolute value bars of z, that's the modulus, aka the magnitude, aka the direction, the length, the size, essentially the square root of a squared plus b squared. And theta is your argument of z, aka the direction. Okay, that can be found doing the tangent inverse of b over a. That's what we talked about last class. Polar form is also called modulus argument form. Modulus argument form, because essentially that's what you have. You have your modulus and you have your argument. The conjugate of a complex number in that modulus argument form is, the only difference is that your theta is negated. One thing that you want to make sure that you remember about the argument is that theta is bounded in between what two values we talked about yesterday? Negative pi and pi, where positive pi is included, negative pi is not. Okay, so it does kind of depend on the direction, which quadrant the complex number is in. So then that way you'll know if you might have to adjust your argument. So what we're going to do is we're going to look at transforming complex numbers into argument modulus form, aka polar form. Okay, so we're going to take these two, one that's purely imaginary, one that's purely real, and then one that has imaginary and a real part. Okay, so remember to go to polar form as the modulus of z CIS theta. So essentially what I need is I need my modulus and I need my angle. Okay. Remember, your modulus is found by doing the square root of a squared plus b squared. Well, what's a in this problem? 0. What's b? So then my modulus is nothing but 2. Okay. Now I need to figure out what theta is. Theta is measured in radians. It has to be in between negative pi and positive pi, with pi included. 2i, if you think about where it's located on the graph, is located on which part? On that y-axis, right? And so remember, when we're in standard form, we start at the positive x-axis, heading which direction? counterclockwise. So what's that angle there? Pi over 2. So theta is equal to pi over 2, or I could have done the tangent inverse of b over a. So it's 2 over 0. So essentially, where would tangent be undefined? That would be at pi over 2. And so to write it in our polar form, it would be z equals 2 cis pi over 2. Cis pi over 2. Questions? Remember, when you're graphing a complex number on this Argand plane, your horizontal axis is your real axis, your vertical axis is your imaginary axis, and this complex number is really 0 plus 2i. So you're not going any distance horizontally, you're only going vertically up to a point of 2 on your imaginary axis. And so essentially, this would be how this complex number would be drawn, like so. The reason why this angle is pi over 2 is because we still start from a positive x-axis heading counterclockwise, and it creates that angle of pi over 2.
Doesn't matter where we draw the arrow?
No, you want to draw that, which one, the blue or the purple? The blue always comes from the positive x-axis, can either head counterclockwise or clockwise, depending on where that purple arrow is located.
So if that arrow was flipped over the x-axis, we have to go all the way.
We would have to go clockwise, because remember, we're bounded in between positive, negative pi and positive pi. So I wouldn't be able to go counterclockwise because I will go beyond pi. So then I'll have to go clockwise, and this will be a negative pi over 2. This one here, our modulus would be -3 squared plus 0 squared, or in other words, just 3. And then theta, we can find by doing the tangent inverse of b, which is 0, over a, which is -3. Or we can figure out that on the, where would -3 be located if you think about a graph? It'd be on the left side, and then it would be, what would that angle be that corresponds to -3? It would be pi. So then theta would equal pi. So then in polar form, our complex number is 3 cis pi. This was a tad bit different. What quadrant is this located in? Because it's not on one of the axes. It would be in the 4th quadrant. I'm just going to draw this picture as a visual. Okay. I've gone over 1 unit. I've gone down 1 unit on my real and my imaginary axes. Okay. So that is where that point is. So when it comes to looking for an angle, I'm going to be looking for this angle right here. So that means it's going to be, what kind of angle is that going to be? It's going to be a negative angle. Okay. Let's find my modulus first though. Square root of a squared plus b squared. What's b? -1. So then my modulus would be √2. And then all I need to do would be define my angle. So I can do that again by doing a tangent inverse of b over a, or I can kind of take a look and say, oh, well, this is actually going to be this particular angle. B is -1, a is a +1. Where in the 4th quadrant, heading clockwise, is tangent of -1? It's going to be negative pi over 4. So then my complex number in polar form will be the square root of 2 cis negative pi over 4. Questions on going from rectangular to polar? So remember, cis is essentially cosine theta plus I sine theta. So when we found those complex numbers, this is the shortened way to essentially write that. If I wanted to write it the long way, it would be the cosine, like that last one would have been the cosine of negative pi over 4 plus I sine negative pi over 4. And then I would have the modulus, which was root 2 on the outside. That is essentially the same thing as us writing root 2 cis pi over 4.
I never put it together. Okay.
Okay? Yeah. So there we go. Questions on this?
No.
All right. No, we know that's what cis is. All right. We're going to convert root 3 cis 5 pi over 6. In this one, we're going backwards. So we're given the modulus argument form, AKA polar form. Now we're going to Cartesian. And remember, Cartesian is Z equals A plus BI, okay? Now this is where you would want to use the more expanded form of what cis stands for. Remember, cis is cosine theta plus I sine theta. Okay, that's what CIS stands for. Okay, so using this more expanded form, you'll be able to write it in Cartesian form or rectangular form. So remember that when we have a modulus in front, okay, it's technically all of this, and then you have your modulus in front as well. Okay, what is our modulus? It's 3, root 3. So then we'll have root 3 times the cosine of theta. What's theta? 5 pi over 6 plus I sine theta, which is another 5 pi over 6. You're going to actually want to figure out what is the cosine of 5 pi over 6 and the sine of 5 pi over 6. Again, unit circle. Cosine of 5 pi over 6 is a negative root 3 over 2 plus, what's the sine of 5 pi over 6? Positive 1/2 I. And so then all we do from here is we just distribute over, and then we'll have our number in Cartesian form. So root 3 times a negative root 3 over 2 turns into a negative 3 over 2 plus, what's root 3 times 1/2? And then we'll have our I, and now we have our Cartesian form.
Oh, that's it?
So we're going backwards when we're going from polar to rectangular. I'm not that confused. All right, let's look at some properties of cis that are gonna be helpful when it comes to simplifying different expressions and things like that. So with your properties of cis theta, when you're multiplying two of them, two different angles, you can technically add them. Division, subtraction, sound familiar? Laws of logarithms. Here, one thing you do need to be aware of is that in any angle of theta looks like it was a multiple of 2 pi, is essentially cis of like a smaller angle that's in between like 0 and 2 pi. K is an integer, so just kind of keep those in mind. We'll look, and you'll see every single property used between now and the end of today's lesson. So you can use these properties to simplify different expressions such as cis pi over 5 and times cis 3 pi over 10. Hopefully you were able to recognize that that involves the very first property. So I can rewrite this as cis pi over 5 plus 3 pi over 10. Well, pi over 5 plus 3 pi over 10 is what? Pi over what? Pi over 2. And then you can continue to simplify from here. Because remember, cis stands for cosine theta plus I sine theta. Well, theta is what in this case? Pi over 2, especially after we simplified it. So this can be written as cosine of pi over 2 plus I sine pi over 2. Because we are simplifying here. What's the cosine of pi over 2? Cosine.
So wait.
0. And then what's the sine of pi over 2? So then this entire expression simplifies down to just be I.
Guessing all the prompts are gonna be like this.
Jonathan, you
Some of them can be.
so correct.
All right. Division means we are going to subtract, and I'm going to subtract theta over rho, which is the top over the bottom. So that's pi over 5 minus 7 pi over 10. What's pi over 5 minus 7 pi over 10? I put cos. Sorry, y'all. I might put cos a few times when I shouldn't put it.
Is it still pi over 2? Negative pi over 2?
It's going to be negative pi over 2.
Does it just turn into a negative pi?
And it is going to just turn into a negative pi once you expand it out. Cosine of negative pi over 2
Still.
plus I sine of negative pi over 2. And that will simplify down to be 0 plus I times negative 1. So then it'll just be negative I. Okay. These are the examples of some easy ones. Yep.
As opposed to the hard one?
As opposed to, yes, as opposed to the hard ones. Okay. Let's simplify. Cis 107 pi over 6. Okay. 107 pi over 6. Huh? It's going to be one of those of a 2K, right? Well, it's an over 6. So this can basically be pi over 6 plus what? What would K be? Like what? Like how could I rewrite this? How does 107 pi over 6 take as the sum of two angles? All right, if I divide 107 by 6, I'll get 17, a whole number 17 and remainder of 5. So that's essentially 17 pi plus 5 pi over 6. When I add those up together, that will give me 107. But in order for me to use the property that essentially says cis theta plus 2k pi, k has got to be an integer, so I couldn't use 17. I could either use 16 or I could use 18 and then maybe do some subtraction.
Why can't do 17?
Because 2k has to be a integer, a whole number. The only way I'm going to get 17 is if it's a fraction. 2 times a number that will give me 17 pi.
Oh, okay, that makes sense.
Okay, so I'm going to use 16 plus an angle, or I'm going to use 18 minus an angle.
16.
Okay. You know, you still have that restriction though. If I use 16, is that going to give me a theta that's in between negative pi and pi?
Wow. Yeah.
Because already at 17, I'm at 5 pi over 6. So if I decrease it, it's going to increase the remainder. So
18.
if I do 18 pi, then all I would need to do is subtract how many pi's over 6's?
1.
1. Okay, so this will follow this particular format. Okay, so this property that says this is just equal to cis theta. Again, we want theta to make sure that it falls in between that negative pi and positive pi range. So then this entire expression is equal to cis of negative pi over 6. The reason why it's negative is because of this original. That is what theta is. So then it simplifies down to be the cosine of negative pi over 6 plus I sine of negative pi over 6. That's in your fourth quadrant. What is the cosine of negative pi over 6?
Isn't it positive? Oh, yeah.
Positive root 3 over 2 plus, oh, so minus 1/2. And I can't go no simpler than that. So that's using all of your properties of cis theta.
Would it be wrong with me to just say square root 3 and then minus 1 over 2? That's what, can't do that? No, you cannot.
You could.
You could do it like that. The I would have to be in that numerator. It can be on the side. Questions on the properties? Now let's continue to use the properties of cis to find the transformation which moves z to iz. Okay, we're going to use transformations, and I'm not talking about like vertical stretch and horizontal translation, things like that. No, I'm talking about like when you're dealing with transformations of complex numbers, vectors. You're talking about like rotations, translations, dilations, like old school geometry transformations, not function transformations. Okay, because vertical stretching, horizontal shrinking, all of those are function transformations. These aren't functions. So keep that in mind. All right. Z, that is that complex number. Okay. But we're using properties of cis, so we want it in polar form. How do I represent complex number in polar form?
Modulus is
Okay. And the modulus is equal to, I know it's equal to the square root of a squared plus b squared, but what does that represent? Yes, it also represents that it does. What else does it represent? Remember, your modulus is essentially the radius of your, so we could use it as r as well. So if you see it as r, don't be confused. I'm going to use r right here because I don't want to have to keep drawing these lines and everything like that. The less z's I can write, the better. Okay, so those are interchangeable. Modulus is essentially the radius of that vector on the circle, or for that point on the circle. Okay, so I'm going to use properties of cis to transform this to iz. Okay, well, I is what? I is not equal to b, no. Yes, it is the square root of -1. Okay. It's an imaginary number, right? It will correspond to what if I were to look at a Argand plane?
The
horizontal axis.
It'll be the vertical axis. Okay. That would have a modulus of what? A little louder. 1. And an angle of what? Pi over 2. So remember, we're using properties of cis to find the transformations that move z, r cis theta to iz. So we need to know what I is, so that way we can multiply 2z. Okay, in order to use the properties and involve multiplication, we need I also to be in the form of, also to be in polar form. So I have a modulus of 1, which I'm not going to write, cis theta, which is going to be what? Pi over 2. So when I multiply I and Z together, I'm able to use my properties to multiply R cis theta with cis pi over 2.
Why are we multiplying those two together?
I'm trying to figure out the transformation between Z and IZ. So that's literally I times Z. And using your properties, when you multiply, you're technically doing what? You're adding. That R is not going to affect the adding process of your angles, which are theta and pi over 2. So this right here represents the expression for I times Z. And if you can look between the original Z and now I times Z, you have a particular type of transformation. Remember, we're not talking about vertical stretching, horizontal shrinking. We're not talking about those because those are function transformations. So we're talking about original transformations such as dilations, rotations, reflections, translations. It's a rotation by what? That hasn't changed. You still got to say how it's rotating. Which way? Counterclockwise. How far? Not theta. Pi over 2. So you have to compare. The only difference between Z and I times Z is this part right here. Originally we were at theta, some angle, but now we've added another 2 pi radians going in the positive direction. Remember, positive means we're going counterclockwise along the unit circle. How far? Pi over 2. And if we're turning, that's technically a rotation. Questions?
Can we assume that it's a rotation if it's the only difference is between the theta?
A dilation would affect the size of your modulus. So like, let's say this went from R to a 2R, then that would be a dilation by 2. I don't know how it would be possible if there was anything on the outside, then that would be a translation of however many units, okay?
So those are the only 3.
Reflection.
Reflection.
So one term from a positive to a negative, then that would be reflection.
So the reflection, then the.
There's units of a pop quiz coming up.
Let's go
Next thing
back.
you know it.
Yeah, I should know. At this point, if you don't know, then I mean, you might as well just kiss your circular function section goodbye. Jesus, come on now. The complex number in this. The complex number Z is multiplied by R cis theta, and its modulus is multiplied by R, and its argument is increased by 0. Not 0, sorry, theta. All right, so we're gonna look at this example. We're gonna write Z equals 1 plus √3i in polar form. And then we're gonna multiply Z by 2 cis pi over 6. And we're gonna describe the transformations that have taken place when we multiply by 2 cis pi over 6. So how do I write Z equals 1 plus √3i in polar form? Yep, 1 squared plus √3 squared. What happens when you square a square root?
Just-
So this just becomes 1 plus 3, which is 4. Square root of 4 is, so that's my modulus. Then I'll have CIS. Then I need to do my angle. What's my angle? Pi over 6.
Mhm.
Because you're looking for where a tangent is a square root of 3 over 1, so just a positive square root of 3.
Be 3/2 divided by half.
So it should be root 3 over 2 divided by a half, so not pi over 6,
What?
It's probably.
pi over 3, because it's y over x.
Sorry.
Mhm. So we need that correct complex number, because now we gotta multiply by 2 cis pi over 6. Remember, when you're multiplying, applying your properties means is that, what am I gonna do to the two angles? Gonna add them. What about the numbers on the outside?
Don't we do that later? Or,
We just multiply them. Yeah, so this becomes 4 cis, the sum of pi over 3 plus pi over 6. What's pi over 3 plus pi over 6?
4.
So pi over 2, okay? And so this essentially breaks down to be, as we know, this will be 4, then cosine pi over 2 plus I sine pi over 2, which is what? It would just be 4i, because cosine of pi over 2 is 0, sine of pi over 2 is 1, so that's essentially be 4 times I, which is just 4i. So that's our answer to B. So looking at the original Z, which was 2 cis pi over 3, and what it was after we multiply, which was just a 4i, we have to describe the transformations that took place. So what happened to the original Z? Or if you want, you can look at it as 1 plus root 3i. You can look at it that way. What happened? So dilation by 2, how'd you get 2? And then it became 4 cis, yep. So originally 2 cis, and then it became 4 cis, so it's a dilation by 2. What else? A rotation counterclockwise by pi over 6. How do you know? Exactly. It originally changed right here, took theta and added a pi over 6. Good. So this is our answer to part C. This one's B. This is A. Questions with the properties? We're gonna look at 1 more, 2 more, and we'll look at Euler's form. So using complex numbers to write cosine of 7 pi over 12 and sine of 7 pi over 12 in simplest radical form. Working with the properties. So writing cosine 7 pi over 12 and sine of 7 pi over 12 in simplest radical form. A complex number that has sine and cosine in it is written in what form? The cis form. So that would be our polar form. Okay. Only downside is that, well, not necessarily a downside, but cis expanded out would be cosine 7 pi over 12 plus I sine pi over 12. Huh? All right. Downside is 7 pi over 12 on our unit circle. No. So is there a way I could get 7 pi over 12? That addition property, that identity that we learned back with circular functions, where if I have an angle, I can create it to be the sum of two angles or the difference of two angles. Since I want them in radical form, simplest radical form, I definitely want values that are on my unit circle. So what two angles can I add or what two angles can I subtract that will give me 7 pi over 12? Two angles add to give you 7 pi over 12 or subtract.
It doesn't give you the 12.
So pi over 3 plus pi over 4. Very good. And remember, when you are adding with the properties of cis, you're technically what? Multiplying. So this becomes cis pi over 3 times cis pi over 4. And since it's their own entity with their own angle, that's the same thing as saying cosine of pi over 3 plus I sine pi over 3 times cosine pi over 4 plus I sine pi over 4. I'm trying to get this in the simplest radical form. So at this point, I probably want to find the cosine of pi over 3, sine of pi over 3, cosine pi over 4, sine pi over 4. You're already small handwriting?
Oh,
I
yeah.
was gonna say, and
It's
or
gonna take up
does
a little
Anderson
bit
even
too much
more?
space sometimes.
What is the cosine of pi over 3? 1/2. What is the sine of pi over 3? So 1/2 plus root 3 over 2I. That's going to be multiplied to the cosine of pi over 4, which is, and then sine. All right, so when I multiply these out, I'm going to have to do old school FOIL. So this will give me root 2 over 4 plus root 2 over 4I plus, what's root 3 times root 2? Root 6 over 4I, and then plus root 6 over 4I squared. When I FOIL it out, what's I squared? -1. So technically, in simplest radical form, I need to kind of combine my reals with my imaginaries. So root 2 over 4 minus root 6 over 4. Again, I get the minus from I squared. They will go together. Then I have my i's, which I'm going to factor out. And I have root 2 over 4 plus root 6 over 4. Unfortunately, I wouldn't be able to fully add them together just to get one fraction because the only way to add radicals is if they're the same. And now I have the simplest radical form for both of these. Cosine of 7 pi over 12 remember, is the real part of a complex number. So the real part would be √2 minus √6/4. But then sine of 7π/6 would be the imaginary part, because sine is always attached to your I. So then it would be √2 plus 6/4.
Why?
This is just another way to do it. I mean, you could do it using the identities and the addition identity. You would do it twice, one for sine, one for cosine. You could do it that way. But you can also use, well, it said to use complex numbers, so that's why we did that way.
So it equals the same thing as with the identity?
Mhm. But it said to use complex numbers, so.
Okay, I mean, yeah.
I want you guys to try these on your own. Find the modulus and argument of these three. So you have 2z. What you do with that 2? Of course. So when you multiply, it becomes 2 √2 cis theta. So if I'm looking for the modulus of 2z, it's technically just what? 2 √2. And then your argument of 2z would just be the angle, which is,
Theta?
that's it.
Yeah, that was easy.
Okay,
Oh.
that was it.
I thought we were
Yeah, I got it.
assume that because it was that, it was actually square root of 8, which would have
Yeah,
to
that's what I
be
did.
2 squared plus 2
So I got
squared,
3
and then
equals
it was 2/2. And then I was like,
No,
arctan of 1.
Look at the form, look at the form, because remember, this right here is your modulus. This is your argument. Okay, so if you do any type of adjusting to it, you just do it to the polar form.
Okay, I got theta equals 1.
No.
Whoa.
Gotta equal it out. All right. So then you have z over I. Well, we already know that I is what in polar form? We went over it.
Your song.
This one here.
Not cis 1/2, but cis pi/2, the angle. Okay. Remember, when you're dividing, what do you do to your angles? You subtract. So this becomes √2 cis theta minus pi/2. So my modulus of z divided by I is going to be √2. And then my argument of z over I is just what? This one here, it's a little bit of work because we've already seen this one for today. It's in the 4th quadrant. All right. I do need to figure out what my argument is though. Oh, yep, I do need to figure out what my argument is of this first part. What is that? √2. What's the angle? But I had to go clockwise, so it's negative. So I minus 1, that is actually rectangular form being multiplied to a polar form. So I need polar form times polar form. So I use √2 cis pi negative pi/4. So in that way I can multiply it to √2 cis theta. What's √2 times √2?
2.
And then when I multiply with my properties of cis, I should do what to the two? Add them. So now that I actually have my most simplified form, I can actually figure out that my modulus of 1 minus I times Z is equal to 2. And my argument of 1 minus I times Z is equal to what? Yep. Questions on polar form? Euler form basically says for any theta, e raised to the I theta, so I and theta are in your exponents, is equal to cosine theta plus I sine theta. So essentially, a polar form can be simplified into e raised to the I theta, and that's Euler form, okay? How Euler form is written is the modulus of E I theta. That's how it's written. So it basically replaces the cis theta that we've been working with in polar form. Okay? So the example that I have for you is 1 plus I theta. 1 plus I theta, which is located in which quadrant? First. Right? Positive 1 on my real, positive 1 on my imaginary. Okay. What would be my angle here? What would be my theta? Pi over 4. Because it would be tangent inverse of 1 over 1, which is pi over 4. What would be my modulus? Huh? Square root of 2. Remember, that just represents the length. Okay. So then in Euler form, it would just be root 2 e to the I pi over 4. Yes, the I comes first. Don't know why, it just does. It just does. Okay.
You're putting it wrong.
I like pi over 4.
Okay. This is another way to write a complex number. This is Euler form.
Why would we do it?
Why is E such a special number?
So instead of it being just modulus cis the angle, this is polar form. But if you see it like this, it's essentially the same thing, just written in a different form.
So can you evaluate that like you can evaluate the polar form?
Exactly. So if you were, and that's actually better too. Look at you, reading my mind. Look at you, reading my mind. Okay. Yes, you can evaluate just like how you would evaluate it in polar form. Okay. Just like how you evaluate in polar form. Those are gonna be the last two things that we do today before you guys head off to lunch. Oh, I'm missing a whole angle here. Sorry, missing a whole angle. My mistake. And so then you have to basically say to yourself, okay, well, I know that this is equivalent to cosine theta plus I sine theta, which means that theta would equal what value? Based off of this problem? Careful.
No.
Negative pi over 4. So then it would become cosine of negative pi over 4 plus I sine negative pi over 4. And then you just evaluate from there. What's cosine of negative pi over 4?
Root 2.
And what about the sine of negative pi over 4?
Negative root 2.
This will be a simpler process, of course.
But it's it doesn't make sense because it's basically just like you're doing cis. It's just telling you you can take it out of that form if you put in and put it in the other form.
There are multiple forms of different things. Think about it. Vectors, we had component, column, base vector. That don't mean the same thing.
We did, but how do you mathematically get from E to the I theta 2 cosine plus I sine theta.
I'm gonna leave that for your differential equations teacher, and when you go to college to teach you that. Remember, trying to get you to through all the curriculum in our window. All right, let's look at this one. That's not a typo. That is base I raised to the negative I. There's no angle there. Okay.
Well,
That's stressful.
No, it's not. No, don't stress. Don't stress. Why should you not stress? Because I is equivalent to what? Like what's like oh, what am I trying to say?
1
Cis,
tan
cis,
Is essentially cis pi over 2, right? I is essentially cis pi over 2, aka 0 plus I, if you look at it as like the full imaginary number. And so this can be the cosine of pi over 2 plus I sine of pi over 2. This can be written how? So I, which is cosine pi over 2 plus I sine pi over 2, can be written as E raised to the I pi over 2. So I can replace this I with this expression to essentially get E raised to the I pi over 2 with a negative I there.
would be negative I squared.
So you would multiply those because it's a power to a power. So this becomes negative I squared pi over 2. And what's I squared?
-1.
Negative 1, but with the negative makes it a. So this becomes E to the pi over 2. And that is I to the negative I evaluated. That's Euler form. But essentially the same things you can do in polar form, you can do in Euler